20 lat temu, jako student pierwszego roku na Wydziale Fizyki, miałem niezwykłą przyjemność uczestniczyć w wykładzie wybitnego naukowca i osoby, która zrobiła mnóstwo dla popularyzacji nauki i myślenia naukowego. Dzisiaj, jako prodziekan Wydziału Fizyki do spraw studenckich, mam niezwykłą przyjemność powitać tego samego gościa, który wracał do nas wielokrotnie, zawsze przynosząc wspaniałe wykłady. Ladies and gentlemen, 20 years ago, when I was a freshman at the Faculty of Physics, I went to a densely packed auditorium to attend a lecture of a very important physicist and a person who has infused the general public with many inspirational thoughts. We have had the privilege of that person visiting us over and over again, and we benefited a lot from his presence. Let me ask Piotr Sułkowski, the person who conceived and tirelessly organized the Ask the Physicist series, to introduce our guests.
Thank you. Będę mówił po angielsku, ponieważ wykład też będzie po angielsku. So I will speak in English because the lecture will be in English. And I think no one has no doubts that the speaker today will be Professor Roger Penrose. I will just say a few words. He defended his PhD in 1958 in Cambridge, which is a little more than 50 years ago. So since that time, he has had a tremendous impact on the whole physics and also mathematics. He is interested in physics, mathematics, mathematical physics, but also other fields, for example, in how our mind works. And recently, yet other fields, like, as you can see in the title, he's interested in fashion and fate and fantasy. So this is something we will hear today. Other results of his work that you might have heard of include, for example, twistor theory or cosmic censorship hypothesis. And you might have seen so-called Penrose stylings. So many results of his work are named just after his name. And he has been awarded many times with many prizes, so it's not possible just to list them all. Let me just say that he is the honorary doctor of our university and also of many other universities. And as we just heard, he already gave several talks in past 20 and even more years in our department and university, and today is the next occasion. So let me introduce Professor Sir Roger Penrose.
Well, thank you very much for that introduction. It's a very great pleasure for me to be back in Warsaw. It wasn't that long ago I was here. It was earlier this same year, the last time. And I always enjoy it and see old friends here. This is the title of a book which I have recently had published by the Princeton University Press. And I gather it's in the process of being translated into Polish. So if you don't understand my talk today, you can, at least in a few months, have the opportunity to read it in your language. Anyway, so let me say something about this. Let me just see if I need something else here. Fashion, faith, and fantasy. Well, each one of these words describes something about a particular area, or perhaps several areas, of physics. And the first one, fashion, has to do, well, string theory, but most particularly, really, the idea that space-time might have more dimensions than the four that we experience. That's 3 space and 1 time are what we directly experience. But according to many ideas in theoretical physics, there may be hidden extra spatial dimensions. And I'll come to that in a minute. The faith has to do with quantum mechanics. There's a very great difference between the first subject and the second. The fashion in string theory, it's not quite as much as it was when I gave this title to the press 13 years ago it was. You see how quick I am at writing books. It took me 13 years, but this eventually happened, fortunately. The fashion part had to do with, as I say, string theory primarily. And one of the features of string theory is that it has a lot of very elegant features and things which attract many physicists. But with regard to evidence in the world that we see, it's really zero. So although there's the hope that some of these ideas will be reflected in the actual action of the physical world, that we don't see that, and there may be one reason or another for that. I'll come to that a bit. In the case of the faith, it's a completely different position, because the faith refers to quantum mechanics. Now, quantum mechanics is an extremely well-supported theory. There are a tremendous number of observations which support the theory. There are many, many things which you can't be explained without quantum mechanics. The faith there, though, however, is that the theory, since it has such tremendous support, many people believe that it must be an absolute truth. And one believes, often you find most physicists, I think, believe that it is an absolute truth and that the theory must hold at all levels, not just the very tiny level at which particles behave and molecules behave and so on, but also at all levels. And that is the faith. Does the subject really apply at all levels? The fantasy, well, that applied originally to certain ideas in cosmology, which I was not happy with, and some of these ideas are still very popular, in fact, even more so, I think, than when I was worrying about them 13 years ago. I have a slightly different attitude to the fantasy, partly because in the meantime, after the lectures I gave in Princeton and now, or when I wrote the book, I produced an idea of my own which could be described as just as fantastical as those that I was rather complaining about. So I have to change my view a bit and say, well, fantasy's all right, it just has to be the right fantasy. I'll come to that one also. Let me start talking about the specific, I hope I can get this machine to work properly. This is I'll be showing you pictures which are from the book itself. So these are unadulterated pictures from the book. Not all the pictures, of course, I wouldn't have time for that because there are well over 100, I forget how many exactly, almost all of which I drew myself. Some are taken from other books as well, or some are about half of them are completely drawn, particularly for this book. Now, what's this about? This has to do with a fashionable theory which held round about at the time of Plato, so you have to go way back. And this was the sort of idea that people had about what they referred to as the four elements. These were represented by what they then knew as the four regular polyhedra. We have let's see if I can get this pointer to work. I'm not sure I can see very well. Here we are. The one at the top left is the tetrahedron, which represented fire. Then this is the octahedron in the middle, which represents air, or if you like, gas. And the one at the right represents, at the top right, that's the icosahedron representing water, or fluid, if you like. And then there's earth, or solid material, which is the cube on the bottom left. And then, of course, somebody discovered the dodecahedron as another one, so they had to think of another element. And that's the thing that you can modify your theory, I suppose, when you find something which doesn't quite fit with what you had before. It's a good scientific position to take. And this had to have another element, which was the sort of ether. The idea was that the material of the cosmos was in some sense different from that on the Earth. We don't believe that now, but this was the view that people believed in ancient Greek times. So, I've moved this not deliberately. That's the sort of thing that's liable to happen with me. So these were as far as I know, there is only one prediction of this theory, and that is if you take two sticks, the stick is a solid thing, so it's made of the earth, and Earth means it's just a solid material, I think. And if you take two of them and rub them together in the right way, you'll get fire. And, well, you see, if you take two cubes, you can cut them up so that they make into two tetrahedra, and that's the fire. Rub the sticks together to make fire, and an octahedron, and that's the smoke. And so as far as I know, that's a prediction of the theory, or maybe a retrodiction of the theory, I'm not sure. But that's the only one I know. So the theory didn't last, or it probably lasted for a great many, I'm not sure how long it lasted, actually. There was a better theory of fire when the phlogiston theory came along, it's sort of anti-oxygen theory, that fire was negative oxygen. That was really rather disproved by Lavoisier. So fashionable theories have had their place in historical context. Now, what about today? Well, let me talk about these pictures first of all. These are meant to be what are called Feynman diagrams of basic processes when particles come together and make other particles. I have in this picture time going from the bottom to the top. If I was a particle physicist, I would have the time going from left to right. Occasionally, my time goes from left to right, but in most of my pictures, time will be going from the bottom to the top, and that sort of marks me out as somebody who works in relativity theory. That's the usual thing. Now, you see the first one is you see two particles coming together and making another one, and then splitting up into two particles as time progresses upwards, and you have different possibilities here. Now, each one of these diagrams represents a basic physical process with particles behaving in this way. And each one of them stands for an expression, a mathematical expression. And it works very well. It's a very powerful way of talking about particle physics, quantum field theory. The one at the end has the little problem. In fact, when you're really talking about quantum mechanics, you've got to have these loops in the picture where they don't. These other ones are what are called tree diagrams, which don't have closed loops. But when you have closed loops, that's when you get powerful results about quantum mechanics, but they have the other problem that as they stand, they represent infinity, which isn't a very good answer. So you have to have tricks for getting around the infinities. And there are all sorts of tricks, and when you use these tricks, you can get excellent answers. So this works extremely well. Now, because of these infinities, you've got to use tricks, and it would be nice to have a theory which didn't have the infinities. And one idea that came along in the 1970s was this thing which was called string theory. So you have to imagine these little lines which represented the history of particles, time going upwards, so the history of the particle is a line. And if that was instead a little loop, then the history of that would be a tube. And then instead of having these sort of awkward corners which lead to expressions which give you these infinities here, you can have nice smooth joins. And this was the very attractive, beautiful idea which was introduced, based on an idea of Veneziano. And this was a Japanese-American physicist called Nambu, basically, who started this off. And it relates to very beautiful ideas in mathematics called Riemann surfaces, and ties together the fact that you hope to get finite answers, and in a lot of respects you do, and this beautiful mathematics. So it's, and when I first heard about this from an American mathematical physicist called Lenny Susskind, I found it an extremely attractive idea, and I was quite taken with it. And that was fine until people found that the answers, you got into trouble unless the number of dimensions of space was not 4, of space was not 3, but 25. So space-time had to be 26-dimensional instead of 4-dimensional. And when I heard that, I said, well, that's no good. Go somewhere else. But on the other hand, the people who were putting these ideas forward were very much still taken with this idea and tried to say, well, you can make sense of a theory in which space has 25 dimensions. And really, the idea here was to have the dimensions as what they call very small. The picture here is of a hose pipe, And so you've got to imagine that the analog of the pipe, as seen from a distance, you imagine you're a long way off, and it looks like a one-dimensional thing. Think of that one dimension of the string as an analog of the 3 dimensions of space. And the thing is that when you get close to this pipe, you can take your magnifying glass, and this magnifying glass, you can see with it that the string is really a 2-dimensional surface. So it's got an extra little loop, if you like, that goes round to make it from 1 dimension to 2. And that's an analog of the idea that people had, that if that dimension was very, very small, in the sense of making a little tiny loop, then you wouldn't see it on a big scale, but nevertheless, the extra dimensions would be there. So it's a nice idea, but nevertheless, it didn't appeal to me very much for reasons which I'm going to come to. In fact, that's probably the next thing I'm going to say. I'm going to give you a little bit of mathematics. This is the only bit of a little calculations and things which I'll be talking about, but let me say something about it. It's really very basic arithmetical ideas to begin with. Think of raising a number to a power. So at the top here, we have a raised to the power b. What does that mean? It means a multiplied by itself, b times a to the b. That's fine. You use things like that a lot. But suppose I want to do this once more. So I say a to b to the c. And when I write it like that, I mean a to the b to the c. So it's a to the power b to the power c. I don't mean the other way around, which would be to bracket the other way, a to the b to the c, for the good reason that if I did it that way, I wouldn't need to write it that way, because a to the b to the c is a to the bc. That's the line that I have, the third line here. So what I do mean is a to the b to the c. In other words, a multiplied by itself, b to the c times, in other words, b multiplied itself, c times. You have to get your head around that and all that. But now, here we have an example of this. This is a thing called a googol. This was a mathematician called Kasner, who had a nephew, and his nephew wanted to make a very, very, very big number. So he said, suppose you write a number like 10, 100,000, but instead the number of zeros is 100. And that was, he called it a googol. And you write that 10 to the power 100. So that's a pretty big number. You might say, why would one be interested in numbers that size in talking about physics? Well, there's one good reason. In my book, I talk about numbers about that size, because that is the number of years, roughly, very roughly speaking, that the biggest black hole that we know of in the universe will take to evaporate away by a process known as Hawking evaporation. See, black holes are things that sit there and they swallow stuff, but if you could wait till the universe expands and expands and expands, then this black hole turns out to be just a little warmer than the rest of the universe, and so it radiates away, and eventually it will radiate itself away completely. And this is an idea that came from Stephen Hawking's considerations and some other people's. And but if you want to know how long the most long-lived of these black holes would be, it's something like a googol years. So you get a feeling for some use that this number has in physics. What about the googol, the one underneath it? That's a googolplex. Well, this nephew of Kasner was not altogether satisfied with a number only as big as that. And so they tried to find a number even bigger than that. And I think the original idea was the number where you write down zeros until you get tired. That didn't seem to be a very good mathematical notion. So the suggestion was you write the number of zeros are googol zeros. Well, you see, 1 followed by googol zeros is 10 to the 10 to the 100. That's a really huge number. And what on earth is that number going to play a role? Well, it does play a role. Well, not quite. There's a number a good deal bigger than that, actually. When I say a good deal bigger, if you raise that number to the power, a million, 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 that number does play an important role in what I say in the book. Well, I'm not really going to explain that very much here, although I'll come to it a bit later in the talk. But that's what's called a googolplex, is 10 to the 10 to the 100. Okay, now I want to do something else now. I want to make a point about these double exponents. when you raise a number to a second power, you see you've got a double exponent, as we have in these 10 to the power, or a to the b to the c. If these numbers are a reasonable size, it turns out that the bottom one really doesn't matter a hoot. It's the one at the top which is all important. And I just want to give you an example of that here. This thing has a habit of jumping just when I sort of wave at it. I don't quite know what it does. It's very sensitive. But this is an example at the bottom, you see, where I say a to the b to the c. Really, c is all important, and it hardly matters about what a is. And a good example of that is this number, which I said was the number 10 to the 10 to the, well, I say it was a googolplex to the million. It's 10 to the 10 to the 124. And that is, roughly speaking, the unlikeliness of the Big Bang, in a certain sense. Suppose you had some great explosion, in the sense that the Big Bang is supposed to have been the origin of the universe, this explosion, and there are all sorts of different ways that thing might have been, this initial explosion. It could have been this or that or the other one, and the one it actually was is a very, very special one. And how special was it? Well, roughly this number, googolplex to the million. Now, achieve that is 10 to the 10 to the 124, which the point is that I want to make here is, suppose I replace that first 10 by a 2, it almost makes no difference to the top one. The 124 just goes up to 124.5 something or other, so it's almost the same, whereas I've completely changed this 10 to a 2. So that's an example of the top index being all-powerful, and you have a lot of flexibility. This bottom number shouldn't really be 10, it should be E. Don't worry about that, but it's, as you see, it doesn't make much difference. Okay, let me see if I can move on to what I want to say. See, I want to talk now about when these numbers become infinite. That's really the point of what I want to say, not the big numbers that they can be when they're finite numbers, but what do I mean when they become infinite? I want to say a little bit about a theory of the infinite. Now, some people here may know of Cantor's idea of the infinite. You can actually count the smallest infinity is the number of whole numbers, the number of integers, the positive number of positive integers, 0, 1, or non-negative integers, 0, 1, 2, 3, 4, 5, etc. And the question, this is a big thing that Cantor showed, is suppose you have not just one number, but two. You see, suppose you have two natural numbers, whole number, non-negative numbers. Are there any more of them than just one of them? Well, no, there aren't any more, because you can count them by this sort of diagonal process. You whittle your way through the picture. The picture here represents all the pairs of numbers, imagine it going off to infinity, but you can count them all with just a single number by wiggling yourself backwards and forwards like this. This was an important thing that Cantor did, and there's something about this thing moving when I don't mean it. Sorry about that. Cantor's theory of the infinite, if you have pairs of numbers, there are no more of them, or 3 of them, or 4 of them, and you get no more than you had before. But if you have something which is a bit different from Cantor's, let me go back and just say something about this counting here, which wiggles its way back and forth. You see, in a certain sense, it's not very continuous. Look at the 2 right up at the top left here. You have to go a long, long way, all the way down there and then back again, even though these 2 pairs are quite close together. So it's not continuous in that sense. You can have 2 pairs which are close together, but they're a long, long way in the counting. So it's not a continuous description. It's discrete anyway, but all I mean, let me just go on and say what I'm saying here. I want to talk about when these numbers become infinite, but in a way where you have to worry about the continuity of them. And if I write this symbol infinity like this, that's infinity to the power 1, that means, in a certain sense, the number of points on a line, a straight line or a curved line, and that's what I mean by infinity to the 1. If it was on a surface, then the number of points on the surface is infinity to the 2, infinity squared. You need two components to describe the number of points on a surface. Then if it was on a 3-dimensional space, it would be infinity to the 3, and n-dimensional space, infinity to the n. So I wanted to use a notation where I worry about the continuity of the numbers. These ideas were actually really introduced by Élie Cartan in the early 20th century, roughly speaking. All the ideas also go back to the Italian geometers, where they talked about ideas like this before. It's a more refined notion, if you like, than the Cantor, in the sense that you can have bigger and smaller infinities, even though in the sense of the Cantor sense that I was talking about before, they'd all be the same. So this is a little bit more refined. Now, what I want to do is now talk about the raising of the powers that I was talking about a little moment ago, but only with these infinities. Don't worry, I'm going to stop being the mathematics in a minute. So I just want to use these ideas in a particular way, and I'm not going the right way. Here's the right way. I want to count not just the number of numbers in a plane or a curve or something like that, but the number of functions. Now, what is the function? You see, if you have a graph, I have the horizontal, this is the x-axis, if you like, and that's the y-axis. Let's first of all think of them as discrete. X can only take a certain number of values, and y can only take a certain finite number of values. You may say, how many graphs are there? How many functions are there? That is like here, I've got this graph zigzagging and taking different values. For the first value for the b, for the x-coordinate could be a different values, second one a different values, third one a different values. So there are a number of possible functions, is a times a times a times a times a, b times. So a to the b is the number of functions when it's discrete. Now I want to do the same thing when it's a continuous curve. So suppose I have a function described by a curve like this, where these are both continuous. Now they might be numbers in a straight line, or this might be representing a higher dimensional space that way and this way. And then you say, how many of those curves are there? Well, I just use the same notation. I say infinity to the a. Infinity to the a is the one going up this way. That's the number of points there are that way, if you like. Infinity to the b is this way. So it's infinity to the a to the infinity to the b, which is infinity to the a, infinity to the b. Okay, so that's what I'm trying to use this notation to describe the sizes of these infinities in this way. Now, let me give you an example of this. This is supposed to represent, say, an electric field in space. So at each point, you've got a strength of the field and its direction. So I put a little arrow there, which tells you what the electric field is. And the question is, how many possible electric fields are there in this three-dimensional space? Well, you would write that in this scheme. At the bottom, you have infinity. Well, you see, the space is three-dimensional. That's the one at the top here. And the number of components of the field, that is, each arrow can point in, well, you need 3 coordinates to describe the arrow, so that's 3. The bottom 3 is the number of components that your arrow has, that's 3. The top 3 is the dimension of the space. And so that's the notation I'm using here to count fields. So the number of electric fields in 3 space would be infinity to the 3, that's the 3 for the arrows, to the 3, and infinity to the 3, the top 3 is the number of dimensions of the space. And I want to make a point. This is basically the same point I made before, but now when these things are infinite, and the point is that if you have infinity to the a, well, the first point is infinity to the a is greater than infinity to the b. If a is greater than b, that's the number of points in this notation, say in a plane, is greater than the number of points in a line. But more interestingly, if you're looking at the functions, infinity to the a to the infinity to the b, infinity to the a, infinity to the b, is much, much, much greater than infinity to the c, infinity to the d, if b is greater than d. And you remember the one at the top is the dimension. So if you're looking at the number of functions in a bigger dimensional space, it's vastly bigger than the number of functions in a smaller dimensional space. So I finally got to the point I was trying to make here. That is that if you've got fields in a higher dimensional space, there are vastly more of them than there are in a smaller dimensional space. So you've got a theory which has, say, more than 4 dimensions, or more than sorry, let's talk about space dimensions, more than 3 space dimensions, as the string theorists wanted, there will be vast numbers, degrees of freedom there, which completely swamp anything, no matter how big the first lower component is, doesn't matter. It's the dimension of the space swamps everything. And so that's when I heard about these ideas, I was really worried because I didn't see how you could possibly prevent this huge reservoir of vast numbers of dimensions swamping everything and completely provide a physics which is nothing like the physics we experience. So this was the point that I was making. And the bottom thing says, again, it's the A infinity to the A, infinity to the B. If B is greater than D, then this first thing will completely swamp the second one. It doesn't matter a hoot what A and C are. Okay, well, that's the point I'm trying to make. Now let's think about space-times. Well, you see, let's go back to this picture of the host pipe, you see. You see, even though the dimensions are there, they may be small, but if that thing's allowed to oscillate in all sorts of ways, the number of degrees of freedom altogether will completely swamp everything we're familiar with. And that's the problem. Now, the argument that people used to make originally, because this idea is not so stupid, it's based on an idea that was put forward by Kaluza. I'm never quite sure which I'm allowed to call him Polish or not, because he was born somewhere where it used to be in Germany and is now part of Poland. Have I got it the right way around? Yes. So I think I'll call him Polish because it's an excellent idea he thought of, which is that, you see, Einstein introduced, basically in 1915, the theory of general relativity, which is a superb, magnificent theory which explains gravity in terms of a space-time. Now that's 3 space and 1 time put together in a space-time, which is in some sense curved. And the curvature of this space encodes the gravitational field. A fantastic idea, a really beautiful idea, and it's now known to be extraordinarily precise. One thing, for example, a minor part of it is, see, if I have a clock which is sitting down on this part of the desk here, and another one is sitting up there, these will tick away at slightly different rates, which can, by the precision of clocks, be actually measured. And Einstein's theory tells you that the one which is going down a little, but the bottom goes a little more slowly than the one at the top. And that tiny degree of precision, of going slower, is now measurable with clocks. They're so precise. Now, it's a wonderful theory in all sorts of ways, and the discovery of gravitational waves recently is another illustration of how not just that, but the black holes, which apparently swallow each other up and all this, there's good evidence that the theory is really, really precise, as well as being a very beautiful idea, or family of ideas. Now, the idea that Kaluza had was to have a 5-dimensional space-time instead of a 4-dimensional space-time, and you could then describe electromagnetism as well as gravity, so that the electromagnetism, that's electricity and magnetism and light, there's a wonderful set of equations due to Maxwell, James Clerk Maxwell, a Scottish mathematical physicist who produced these equations based on the findings of Michael Faraday. And it's an extremely precise theory and has tremendous applications, and the light theory and everything, and the radio waves and all that stuff are encompassed by this theory. So, but then the electromagnetism affects gravity too, and so you want to have a theory which combines these things together, and Kaluza's idea really did this. Well, it was modified. I mean, the problem was about the extra dimension. Why don't we see the extra dimension? Well, one of the ideas was, and Klein, who was a Swedish physicist who had the idea, and I'm going to, the thing is moving when I don't want it to. I'll come back to that in a minute. The idea was that you make this extra dimension very small, so it's like the hose pipe, if you like, that the other dimension, which is represented by these loops at the top of the picture, the extra dimension is really a sort of circle up there. And if that was very small, you might not see it. That's really not the point, though. The point is that you have a symmetry along the dimensions, so there isn't the freedom in that extra dimension. You can slide the whole thing around in the extra circle, and there, you can't wiggle that independently. So it's really a theory of three-dimensional space and one of time, not of four-dimensional space and one of time. But it's a nice way of encoding the ideas of electromagnetism combined with gravity. Fantastic idea, actually. But the string theorists say, look, well, this theory worked, so why don't we do the same thing and have more dimensions? The troubling thing is there's something very different, because the Kaluza-Klein idea, originally at least, was that you had this symmetry, and so you're not allowed to wiggle the dimensions at the top. The whole five-dimensional space-time was not allowed, the freedom is all in the bottom. You don't have any freedom in the fibers, as they're called. This is an example of a fiber bundle. I'll just show you some other examples here. Well, not examples, but the idea of what it is. So you can think of an ordinary graph, and the bottom, the x-axis can be replaced by some big space, and the y-axis by another big space, and you can talk about fields in terms of these, what's called a fiber bundle. Take the one on the left hand, on the right-hand side, which looks a bit more general. The ordinary space is meant to be the one at the bottom, and then what does a bundle mean? Well, you see, you have a lot of spaces at the top, which in the case of Kaluza-Klein are these loops, but they might be at some other space. So I've drawn into some complicated space. And what is a fiber bundle? Well, it's the bottom space is M, that's called the base space. That could be the ordinary idea of space-time, say that's the bottom one. And then this thing at the top is the idea of as M's worth of F's. You see, the fiber, as it's called, is the space at the top, and you've got, over each point, you've got one of these things. And so the fiber bundle is really an M's worth of F's. I think that's the easiest way of saying it in a few words. And the ideas of the forces of physics can be understood as in these terms. And Andrzej Trautmann here who is really the person who first clearly realized that that's what's going on in the modern ideas of the forces of physics. Well, apart from general relativity, which isn't quite such the same idea, but the strong forces, the weak forces, and the electromagnetic forces can be understood this way. And the Kaluza-Klein picture, which I just had a minute ago, is really an example of that. So I didn't want to say too much about these things here, but the point I really want to make is if it's one of these bundles, all the dimensions are in the bottom, and you don't get any more functional freedom in the fiber because of the symmetry. If you have this symmetry imposed, then you're all right. But in string theory, that's not what you do. What you do is you allow the whole thing to be thought of as a space-time, and that these fibers can wiggle any way they like as well, and then you do have this functional freedom problem. And that was the thing that worried me. It seems to me it doesn't make sense, and how is it that you don't get all these degrees of freedom which are hiding there in the space, waiting to get loose and playing havoc with everything? Well, the argument that is normally made here is that these dimensions require an enormous amount of energy, and that they're sort of immune from being excited because of the amount of energy you need. And the amount of energy you need, I think people have in mind an accelerator, things like the CERN accelerator, which fires particles and at other particles, and you get energy which can be really pretty big. But how much do you need in order to excite these extra dimensions? Well, it depends which string theory you're looking at. But the one that people use now, it would require something like a sizable artillery shell. So you're thinking of a single particle with enough energy in it to make a real mess of this room. So that's the kind of energy that would require to excite that extra dimension. And people say, well, you're not going to get anywhere near that. I was never very persuaded by that, because suppose somebody in the Andromeda galaxy had a really advanced civilization and had produced that, that energy would be to excite the extra dimensions for the entire universe. That's the point. It's not just that you have something here and you hit it with some very energetic particle and it excites it and then that gets the extra dimensions at least. It's the entire, you just get that much energy, and it's that much energy for the entire universe. Now that's, for the entire universe, it's nothing. And here's an example, you see. I just think of the Earth in its orbit around the sun. Well, there's far more energy in that than there is in this artillery shell. It's ridiculous. I mean, I forget how many millions it is more. So the energy is there, but it's ridiculous to suppose that you have to excite it only at one point. Why isn't it spread out? So the picture I have here, these are all pictures from the book. Here you have the Earth going around the sun, and you could imagine that the energy in that could somehow excite or be excited by this energy that is sitting here in the extra dimensions. That's the thing at the bottom here. And if you spread that out over the Earth's orbit, it's a ridiculously small change in that extra dimension. And people say, well, quantum mechanics, it's a definite energy that you would require to excite that extra one. Okay, it's a definite one, but it does almost nothing because it's spread out over this huge tube. So if you want to make any substantial difference to the extra dimensions, you're going to need lots and lots and lots of quanta to excite it. And then you might as well treat it as a classical problem. So that's the argument. If you want to know the details of the argument, you can look in the book. But I just want to make the point that, oh dear, look at this, it's jumping away on me. I think it's sensitive not just to my touching, it's if I wave my hands. Perhaps it's the Maxwell electromagnetic fields that are which are causing this thing to move. Anyway, this is the sort of argument that worries me, and there's no reason, as far as I can see, for these things to be stable in the way that people had thought they would. In fact, I gave a talk about this 2 years before, I think, or 1 year perhaps it was, before the lectures that I gave in Princeton on which the book is based. That was in 2003, and I think I gave a talk, it was one of Stephen Hawking's birthdays, I think it was 65, and I wasn't able to go to most of the meeting, but I went to the last day, and I gave a talk, and I warned people that they might not like it, and I was afraid that I would not get away without being tarred and feathered. Perhaps they didn't have the tar and feather ready, so I did manage to escape. But I was trying to say that these extra dimensions were highly unstable. Not only that because of theorems, these are actually theorems that Stephen Hawking and I had proved, that you would develop almost at once into a singular state, that the extra dimensions would collapse and produce singularity. That means they become infinite and they don't make any sense. So that was the problem, and I was thinking people... Well, the next day, there was a more general meeting the next day, and I went there, and Gabriele Veneziano, who was really the first person to think about this string idea, a very nice idea initially, and he's a lovely chap, I like him very much, and he came up to me and started complaining about something I said. This doesn't work. I said, no, I don't mean that, it's so-and-so. Oh, he said, oh, that's fine. And at that point, Michael Green, who is another big figure of string theory, came up and said, look, what about this? And you do that. And then Gabriele Veneziano said, no, he doesn't mean this, he means this. And they started arguing with each other, so I snuck off. But then I sat down at lunch afterwards, and Lenny Susskind sat down opposite me, and he was the person who first showed me the idea of strings, which fascinated me. When I first heard it, as I say, I thought it was a very beautiful idea. And he sat down opposite me, and he made the following comment, I think word for word, as far as I can remember. You're completely right, of course, but totally misguided. And I was never quite sure what to make of that, but I didn't get him to explain any further. I think it meant, okay, yeah, we know about things like that, but that's not the point. We're going to find the truth, and don't bother us about mathematics and so on. I wasn't quite sure. It's an irony, because so much of what drives string theory is beautiful mathematics. There's no question about that. And also it does have a very important impact on many ideas in mathematics which have changed some of these subjects. But is it physics? That's the point I was worrying about. And I think one of the reasons that string theory is still fashionable, I was rather worried that after all these years, it would have faded away and my book would be about history instead of about the things that are going on in the world still. But fortunately, it's not gone out of fashion. That's not fair to say fortunately, I'm not sure about that one. But fortunately for my book, I should say, it's not gone out of fashion. Although it has to some degree, I have to say. It's not quite what it was. There are many reasons that people are doubtful about the ideas there. They don't seem to have made an impact on the physics of the world that we... Well, it has in a sense, but these are all indirect ideas that have been used in different ideas in mathematical physics, but not as the subject as a whole has not really made any impact on physics as we know it. But what it's very different in the case of quantum mechanics, you see, now I want to talk about the faith. Now, see, quantum mechanics has absolutely enormous numbers of experiments supporting it, completely different. It's the complete opposite. String theory has nothing to support it as a theory in the world. Quantum mechanics has vast numbers of things, not only many things which were totally mysterious before, like the stability of an atom. You see, think of the hydrogen atom. It's got a proton and an electron going around it. And according to classical theory, that electron, as it goes around, would radiate electromagnetic waves, spiral into the nucleus, and there's your hydrogen atom gone. In fact, that would apply to every atom. And that doesn't happen. And it's stabilized because of this wonderful theory of quantum mechanics. Indeed, it is a wonderful theory, and it has its beauties as well, very much so. I just want to show you here the sort of a typical, archetypical experiment, quantum mechanical experiment, where you've got, it's called the two-slit experiment. You imagine some particle source, say it's electrons. These electrons are being fired through a couple of narrow slits at a screen behind. And every time the electron hits it, it makes a mark, say. Well, if you close off one of the slits and you get them, shoot them through the other one, you see this spread, they scatter a bit and concentrate it along a central region there. Close that slit, open the other one. You have a very similar pattern, just shunt it on very slightly by comparison with the first one. Suppose you open both slits, you might expect to just add the patterns. Nothing like it. You find these interference stripes. There are some places where somehow where particles could easily reach previously, suddenly they can't reach those points. They interfere with somehow, well, sometimes you can't, the point P, I think, is one where they can't reach, and the point Q is where you get enhancement. So you get these sort of interference stripes, and the only way, well, I wouldn't say the only way, because there are all sorts of crazy ways people have of explaining things, but the basic way one understands this is that the electron, each electron, somehow has to go through both slits at once. That's a crazy idea, but still, that's the way we think about it. It goes through both slits at once, and those two possibilities interfere with each other. It behaves like a wave, and the wave can go through both slits at once, and depending upon whether the waves cancel each other out or enhance each other, you get the strips, and it works fine. The only trouble is, according to quantum theory, there is no limit. I mean, you talk about electrons, single particles, but it doesn't say single particles. And there are experiments done with, I think the record, as far as I know, is with the C60, C70, Anton Zeilinger and his group in Vienna show you can get these same patterns with sizable molecules. Now, according to the theory, there's no limit to the size. What about a cat? Well, you see, why do I say a cat? Well, this is a version of Schrodinger's famous cat. Well, Schrodinger's cat was dead and alive at the same time. I wanted to have something a little more humane. It wasn't so much the humaneness, it was I wanted to have it a little bit analogous to the two-slit experiment here. So here we have an experiment where the cat is going through both doors at once, like the particle going through two slits at once. And the way we do it here is we have a laser up at the top left here, which fires individual high-energy photons. These hit what's called, oh dear, it's going again. I'm not mastering this, I'm afraid. I should keep my hands away from it. There's a beam splitter at the left, which you can think of that as a half-silvered mirror. Let's start it again. Oh, dear, dear, dear. It both goes through, and you see, a beam splitter, think of it as a half-silvered mirror. Half the light goes through, half the light is reflected. But at the level of a photon, the photon goes through and is reflected both at once. So it's like the particle going through both slits at once. But now it's reflected and transmitted at once. And if it's transmitted, it opens the door A. If it's reflected, it opens door B. And since, now here's the point that Schrödinger was making, his own equation tells you that this extends to every scale. So there's a thing called the state vector or the wave function, which Schrödinger's own equation describes, and the way his description works is what's called linear, and that means that if you get this splitting of the two alternatives of the beam splitter, that must continue right the way through, so that not only does the photon go through both ways, share its existence between two roots, but the door A, which is triggered by this thing at the top, is open when it receives the photon, and B opens if it receives the photon. And the Schrödinger equation would tell you that the two doors must be, well, the superposition of door A being opened and B closed, or B opened and A closed. And here's the cat now trying to get the food, which is inside the room. And, well, the cat has to be a superposition of seeing one door open and going through that door, and seeing the other one. It's like the particle going through the slits, you see. Schrödinger introduced his cat, dead or alive or whatever it was, but in this case, really to show that his equation didn't work for a cat. So he was more or less saying that. I think people take his cat in a different way. They say, oh, well, no, if you made a proper experiment, well, then the cat would be dead and alive at the same time. And Schrödinger was really saying, no, he was saying, if you follow my equation, that's Schrödinger talking, you get this nonsense. Something must be wrong. And so that was his view. It was certainly Einstein's view that something must be wrong. And it was certainly de Broglie's view, who really showed that particles behave like waves under certain circumstances. Even more remarkably, it was Dirac's view. And you have to look a little more carefully because Dirac didn't often speak his mind on these matters. And I had a difficulty finding an appropriate quote, but there is one in the book which I got from a colleague. And I thought it expresses very nicely in Diracian language, which is absolutely clear and precise and childish almost. And you can see, he says, yes, quantum mechanics works marvelously well. The formalism, you can't really argue with it. It gives excellent examples, but it's a provisional theory because it doesn't explain what the world is doing. Something is wrong at some level. So, I know you shouldn't appeal to authority, but I think my view certainly also is that something is wrong. But let me see. Well, what's this picture doing? Well, you see, I think it was early, can't remember the date now, but I was invited by the Hans Christian Andersen Society to give a talk. And I was a little puzzled by this because although I've enjoyed the fairy tales, why are they asking me to give a talk? And then I thought, oh yeah, well, I wrote a book once called The Emperor's New Mind, and the title was indeed based on The Emperor's New Clothes. And I thought, well, I suppose that's the reason. The bicentenary of Hans Christian Andersen's birth was coming up, I think, in a year or two, and there was a series of lectures they had, and they wanted me to give one of these. And so I thought, well, I can't very well talk about the Emperor's New Clothes because that would be not what I'm thinking about these days. So what I'm thinking about is the foundations of quantum mechanics, and I thought a bit what would be an appropriate story of Andersen's to illustrate the foundations of quantum mechanics. Well, I did have a version of the cat Schrödinger's mermaid in the lecture, where it was to do with the mermaid. At one point, when the sun comes up, the first beam of light, so you think of the first photon from the sun, she dies. So what you imagine now is in this version, you put a a beam splitter between that, you see. And so the photon is beam split between going through and hitting the poor old mermaid or going the other way. And so she is a Schrödinger's mermaid. But this is a different way of illustrating the story. And here we have the mermaid, and she is representing the way we do quantum mechanics in a sense. So the top, let me go to the next picture. Now I have to do it myself rather than it doing it for me. The top half of the picture represents the classical world. I'm using the letter C to describe that. And you have things going on which separated objects, and we sort of have a feeling we understand sort of what's going on there. Newtonian physics works pretty well, and that's a view we have of the world. And that's represented by the top half of the mermaid. The bottom half of the picture is the quantum world. I use the letter U, which stands for unitary evolution, more or less stands for the Schrödinger equation. That's the evolution that Schrödinger's equation tells you happens. And it's full of all sorts of strange things, these entangled mess at the bottom, these strange fish, all sorts of crazy things which we don't know, we don't experience, a very unfamiliar world. But the mermaid experiences both worlds. So, as I say, the bottom half is in the quantum world and the top half in the classical world, and she represents what happens when we make a measurement in quantum mechanics. We take the quantum description and somehow it becomes part of this classical world. And so she's rather magical. I call her, well, she represents the reduction of the quantum state, or the collapse of the wave function, as it's called. You have this quantum description, and suddenly you make a classical choice between these quantum alternatives. A good example is the Geiger counter. You think of a particle, and this Geiger counter, if it receives the particle, it goes click, and you can hear it. That's a classical world thing. If it goes somewhere else, it doesn't click. But the particle has to be thought of as feeling out all these different routes as well. And so the click, you might think the click was happening and not happening at the same time. But where you do quantum mechanics is one of these alternatives happens. And the procedure you use involves the quantum state that's described by the Schrödinger equation. You sort of throw it away and make a choice. It's this crazy way of doing physics, but Schrödinger didn't like it at all, and he was quoted as having said in the presence of Niels Bohr, if all this damn jumping, that's the jumping of the state to have one result or another, if all this damn jumping is here to stay, I wish I never had anything to do with quantum mechanics. And Bohr had tried to cheer him up and say, well, no, we really needed you, and all that sort of thing. Anyway, that's the description of what's going on here. It's also, I wanted to illustrate it, that somehow she looks down on the world and brings her experience. There's a sort of play with the perspective a bit. She's looking down on the world, and she's bringing to the classical world some understandings which she obtained from her experiences in the world beneath. Anyway, but this is the crazy way in which we do quantum mechanics. And you see, we have the upper axis. I'm afraid this is the particle physicist's time going from left to right. We have the state going upwards, and so this upper arrow represents the quantum state, and the U represents this thing evolving smoothly according to Schrödinger's equation. And then suddenly you make a measurement, or whatever it is, and it chooses one of the alternatives with a probability. And then that thing evolves, and then it chooses one, and the R represents the reduction of the state. And this is the crazy way in which we do quantum mechanics. It's the way we do it. It's crazy, but it works. Now, I'm not happy with that, as Schrödinger wasn't happy, as Einstein wasn't happy with it. It seems to me, as Dirac said, we need some theory which supersedes current quantum mechanics. When I use the word faith, this is something that people hardly ever seem to believe in the quantum community. They say, oh no, we've got to understand it somehow. No, you shouldn't change the theory. We have this absolute faith in the way the theory works. It works so well. We've got to understand this crazy picture, and that is our failing that we don't understand it. I take a different view, and this is that there is something wrong with quantum mechanics, and I say these other people, I shouldn't appeal to their authority, but I am agreeing with them, that there is something that needs to be changed. I have various arguments. This is an argument which I try to describe somewhat. I have the 3 chapters, fashion, faith, and fantasy. Fashion being the string theory thing, and then quantum mechanics is the faith, and then fantasy is to do with these ideas in cosmology. But then there's this chapter 4 is where I show that there are some alternatives you might consider, other than the ones that are more fashionable, whatever it happens to be, and just to show that there are other routes that one might try going in, and certainly the ones that I prefer to go in. And one of these has to do with the way in which quantum mechanics, I believe, should be modified, and that is how it should be combined with Einstein's theory of gravity. And one of the arguments to show that it needs to be changed is the following. I'm imagining there is some quantum apparatus here on a tabletop. I had to do these drawings, and I was the person at the Princeton Press who was telling me sort of how to make the computer schemes work and all that. And he looked these things over, and he looked at this picture and he said he thought, well, it wasn't terribly clear about this apparatus. I don't think that dial is very clear. Couldn't you make it clearer? And I had to explain to him, this is a completely fabricated experiment. No, I made it up. It doesn't mean anything. It's supposed to be an experiment, though, in which gravity is involved. It's a quantum experiment where you have to take into consideration the gravitational field of the Earth. That's the only gravity involved. It's the Earth's gravitational field attracting, if you like, the elements of the quantum system here. Now, there are 2 ways you might consider describing this according to quantum mechanics. Now, the way that probably most physicists would use is what I'm calling the Newtonian way. You do what's called putting a term in the Hamiltonian. I won't describe what that is, and those of you who know about the physics will know what it means. You put a particular term in your expression, your mathematical expression, and that, like any other force, would be using gravity in the same way as you do everything else. That's fine. And that works, and there's not a problem. But Einstein would say, no, that's not the right way of doing it, because the Earth's gravitational field is just like an acceleration. And you should be really using a freely falling frame of reference, do your calculations in that, and then transform back. Okay, that's the 2 ways of doing it, the Newtonian and the Einsteinian. Well, what's the difference? Not much. In fact, there are experiments. There's famous experiments that tested things like this, and they showed that the answers, it seems to be that the acceleration and Einsteinian view and the Newtonian are equivalent in this. But they're not quite. You have to be very careful about this. There's this thing called the quantum state, or the state vector, or the wave function, and this thing describes what the quantum system is. And when you compare the Einsteinian and the Newtonian way, you find that they differ by what's called a phase factor. You multiply one of these things by this number, which is called a phase factor, and you get the other one. Now, normally in quantum mechanics, you say you don't care about phase factors. It makes no difference. So it's completely equivalent. But then you have to look very carefully at this phase factor. And you see that that phase factor involves the time in a way which is not quite consistent. The 2 methods are not quite consistent. It's what quantum field theorists call you're using a different vacuum. And it's not something you would notice if you just stick to one or stick to the other. So it doesn't make any difference in this experiment. But if you did an experiment which was like what I'm describing here, now here, this is the Schrodinger's cat or Schrodinger's lump or Schrodinger's rock or something. At the bottom, you see that this rock is put into a superposition of 2 locations. The top part of the picture is describing the space-time. So each location of the lump has its history in space-time. And I have used black and gray to describe the 2. And these curves at the edge represent free fall. So if you describe how a body falling in the field of this gravitational field of this rock, it would describe, if it was in free fall, those curves. And they're a little bit different. You see, the gray curve is if it's in the gray position, and the black curve is in the black position. And it's this difference, which is what gives you this difference in the 2 vacua. Now, you see, from normal, well, it's a very small effect. I shouldn't say it's small. It depends on how big the lumps are. If these were just a neutron or some quantum particle, it would be a very, very tiny effect. But if it was an actual cat, it would be a huge effect. And this is just the details. You have to work them out. But the argument is that there is an inconsistency, but this inconsistency takes a little while before it shows itself. And then you're in trouble. And so I have a picture here, which is sort of describing what I mean. It's a little bit of an obscure picture. I hope we can make sense of it. It's a space-time picture, just like the one we had before, and it's jumped for me nicely again. It's like that picture, but now I'm trying to describe the history of it, where the lump was in one place originally, and then you try to put it into a superposition of two locations, which you could do quantum mechanically. And when you have it in a superposition of two different places, like the particle going through the two slits, then each location will warp the space-time slightly differently. And the thing that's being illustrated here is how much is that warpage. You have a measure of how big is the displacement, the difference between those two space-time geometries. Now that will involve two factors. One of them is spatial difference, and the other is the temporal difference. Now the argument that comes from the previous picture I showed you tells you that once this space-time displacement has a volume which is of order unity, 1 or so, in what are called natural units. Now, natural units are the units that, they're very unnatural if you want to use them, but they're natural physically, where you take the speed of light to be 1, you take the gravitational constant to be 1, and you take Planck's constant to be 2 pi. Well, Planck's constant in Dirac's form to be 1. And once you've done that, you can get away with that, just get away with it. Doing that, you have what are called natural units. And in these natural units, this volume that I've ringed here is of order 1. What that means is if you have a big spatial displacement, it'll be a very short time before one of these existences has to die off. If it's a very tiny displacement, it can be a very long time before one dies off. But the argument is that you can't maintain the superpositions when this space-time separation becomes more than order unity in these units. So that's the argument. And I should say that there are experiments which are testing this hypothesis. This one here is a cartoon of an experiment being performed by Dirk Bouwmeester, who is a Dutchman who shares his time in Leiden and in the Netherlands and in Santa Barbara in the United States. And well, he's not a superposition of these two locations, but he flies backwards and forwards by airplane. And the idea is that he's been working on this for, I don't know, a couple of decades, I can't remember now, but he's hoping that within the next several years, he will have an answer. The idea is that you have a photon here, which is something like a visible light photon. It hits the beam splitter here, so it shares its existence between going down this way and going horizontally that way. The horizontal component is kept in a cavity. It's reflected backwards between two mirrors about 1 million times. The other one has another cavity reflected backwards 1 million times, but one of the mirrors is the funny little one. It's a tiny mirror, which is about 1/10 of the thickness of a human hair. And the idea is that this 1 million-fold banging, I've got the universe has shown up on me, banging backwards and forwards on this little tiny mirror, it was enough to move it by an amount which is about the diameter of an atomic nucleus. Not much, but enough that according to the ideas I've just been describing, it should become one or the other in, depending on details, some seconds or minutes. And the idea is that if the thing will maintain itself by a good time longer than that, then this theory goes out the window. If it spontaneously decides to be one or the other, and then you can see that by bringing the photon back again and see whether you've lost coherence or not, then that would support a theory like the one I'm describing, in which quantum mechanics is shown to have its limits. So that would be the quantum faith. If the experiment works out that way, that would be a violation of the quantum faith. So that would be very exciting to know whether this works, what the answer will be. My hope is that it will show that there is some limit to quantum mechanics and that the limit can be measured in this kind of way. I'm rather afraid that if it shows it to be wrong, that everybody will be happy. It shows quantum mechanics still works. If it does show a difference between quantum mechanics and reality, people will say it's a bad experiment. And I'm rather afraid that's what might happen. Okay, now what about the fantasy? This has to do with the universe as a whole. And I was rather worried about certain ideas which are current in cosmology. Some of them look particularly crazy. Some of them look only moderately crazy. You may say that the Big Bang itself is a pretty crazy idea. It is. In fact, we need craziness. So I rather shifted my view between, I think, when I gave the lectures in Princeton and when I finally wrote the book, because I was sort of saying fantasy is a bad thing. But in the meantime, I have my own crazy idea, and I'll say something about that in a moment. And my view now is we need a crazy idea. The thing is, it's got to be the right crazy idea. We need a bit of fantasy, is what I'm trying to say. And after all, quantum mechanics explains things which are really fantastic already. So there is fantasy out there. You've just got to find the right one and the right theory to describe what's really going on. So it's not a bad thing. You've just got to find the right fantasy. I know I'm cheating slightly when I put that forward. This is a picture of the history of the universe, more or less as we understand it, with the time now going upwards, the Big Bang at the bottom, it expands, slows down a bit, and then starts to do this accelerated expansion, which was the thing that was discovered basically in the late 1998 or so by two groups, which they seem to observe this accelerated expansion. People say it's due to what's called dark energy. I call it the cosmological constant, which Einstein introduced in 1917 for admittedly the wrong reason, but it does seem to be something that's really out there. You may ask, what's all this frilly stuff doing at the back? That is because I don't want to prejudice the issue as to whether the universe is closed up spatially or whether it goes on forever. It doesn't matter in what I want to say here. It's an interesting question. The evidence seems to be that it just doesn't, but that may not be right. We don't know. But this is a general picture of the history of the universe. We're somewhere in the middle here, just seeing this accelerated expansion beginning. Now it's done. It's jumping on me again. Now the question that I want to raise is this thing called inflation. If you read any cosmology book these days, popular or technical, they will talk about inflation. Now, inflation is, you might say, why didn't I put it in this picture? Two reasons. One is maybe I did, but it's so small that it's tucked into that little black spot at the bottom. You wouldn't see it on this scale. The other reason is I don't believe it. And I always had trouble with it because it didn't seem to explain one of the major things. I'll come to that in a minute. But let me first of all show you these different graphs. This is just to show that in order to make inflation work, you have to invent something, which is usually a thing called the inflaton field. And the only reason for believing it's there is that it's got to explain inflation. And I just have these pictures just taken from the web, different people's ideas about what or some of the top two of the same person's different ideas, about what the potential function of this inflaton field is. And the point I'm only illustrating here is that they can look pretty different. They may have a general shape which is similar, which is what you want, but the theory doesn't tell you what that thing looks like. It's very artificial. There may be ideas, different ideas which are popular now, which may be a little less arbitrary than this, but I was just trying to point out that it's not really theory-driven in the sense of ideas from particle physics or something. But what about one of the main motivations originally? One of the main motivations was the universe seems to be very uniform and very flat, and this seemed puzzling because if the universe just started off any old way, why does it look so flat? And so they introduced this idea of the inflation, which stretches it all out, this early stage of the very rapid expansion, which is a bit like the expansion that we have in the future here, but tucked into that little point. So inflation, you have to imagine that this exponential expansion, as it's called, took place. There was an earlier stage of it, right tucked into that point at the bottom. I had a lot of trouble with that, not just because it seemed like an artificial idea, but because I didn't think it did many of the things it was supposed to do. One of the things was smoothing out the universe. And the sort of argument I had is the following one. See, here is a picture. The universe probably isn't like this, but suppose it was closed up, certainly the kind of view that people had at one time, and it would start off expanding, and this is represented by this nice smooth origin here, the Big Bang at the bottom, expanding out, and then it comes back again and collapses. But by then, you've got all sorts of mess, black holes and things, and they start running each other, and as the universe gets smaller, they form one incredible mess like that. It might have been a collapsing universe, and again, you end in an incredible mess like this. Now, the thing is that the theory, whether you put the inflaton in or not, is symmetrical in time. So any of these things which you could see happening into the future would be equally probable things that you could have in the past. Now, you see, one of the important laws of physics that we have is the thing called the second law of thermodynamics, which is more or less telling us that things get messier and messier as time goes on. Well, it doesn't quite say that. Things get more and more random as time goes on. That's what it says. Now, this is sort of, but this in process going. It's getting more random as time goes on. But if you try to turn it the other way up, that's what the final picture here is. Suppose the most likely, you see, when it gets more random, this is a very likely state at the end, if you like. Much, much more likely than the one at the beginning. And that was the number I gave you. Remember the 10 to the 10 to the 124. In the old days, I used to say 123. The 124 comes from dark matter, which seems to be well established now. So it may even be 125. It doesn't matter. It matters hugely. It's an absolutely enormous difference, but it doesn't matter for the arguments. And all those horrible possibilities are represented by this mess. So almost all of them would start off with an incredible mess like this. Inflation does you no good at all, because this would include the inflaton field just as well. Does you no good at all, and it certainly doesn't iron it out. You get a lot of mess, which we don't see. It's not like that. It's like this. It's not like the third one, it's like the first one. Why? Not because of inflation. It doesn't do it. Well, there are all sorts of arguments that go on about that, but the short answer is it doesn't do it. This is just to show that with the idea of the second law of thermodynamics, what's going on. It's a thing that takes a little getting used to. It's what I often call the mammoth in the room. You see, second law of thermodynamics, what does it say? It tells you the randomness is increasing in time. Go back in time, it's almost the same thing. Things are getting less and less random. They're getting more and more special as you go backwards in time. What do you see when you get to the beginning? Well, what's the best evidence for the Big Bang? It's this thing called the cosmic microwave background. This is radiation coming in from all directions. It's very, very uniform. Not just uniform, it has a spectrum. It has the different frequencies which reflect a random state. It's telling you what you're looking at is something completely random. Maximum entropy. Well, that's crazy, because entropy was going up ever since then. If it started at the top, how can it be going up? I mean, that's the mammoth in the room as far as I'm concerned. It's not a paradox for the following reason. You see, here we have, imagine these different boxes. This is the second law in action when you imagine a gas in a box. Here we are having the gas initially tucked up in one corner with these compartments. You open the compartments, the gas spreads out into the box, entropy is increasing, the state becomes more and more uniform. Okay, that's what you see. However, what about gravity? Now here's the difference. Suppose we had gravity considered, and imagine now the box is on a huge scale, say a galactic scale box with lots of stars buzzing around all over the place. And now the entropy is going up still, but now they start to clump. The stars form galaxies. Well, it's not quite the way it happened, but never mind. Form galaxies and things like that. And then you form black holes. This is the entropy going up. And what we see is a mixture of top right and bottom left. You see the uniformity. You see that as far as matter and radiation are concerned, it's high entropy. That's right. the way it's low entropy, it's gravity, and pretty well gravity alone. That seems to me one of the big mysteries of cosmology. If you see a cosmology book and says, what are the mysteries of cosmology? You go down the list, blah, blah, blah. It's not mentioned. I find that very strange. To me, it's the biggest mystery of all, and so it needs an explanation. Well, this is just to say how important it is that gravity is there. It's where we get all life comes about because of the sun, and people often say, well, the sun, we get energy from the sun. We don't, because the sun gives us energy, and it gives us light and heat. That goes away in the night. Just as much goes away as come in, more or less. Slightly less goes away because of global warming, of course, but that's a small picture, a small factor in this picture. But the main point is that the sun is a hot spot in the cold sky. I won't go into the details here, but it's the entropy which we gather this because of the uniform distribution of matter there had been initially is clumped into stars. That represents an increase in the entropy due to this reservoir of low entropy in the uniformity, and you get stars, and we live off that the difference between the hot star and the dark sky. That's a long story, which I shouldn't really say too much about here. But the point I want to make first is the black hole. So we had a picture of the black hole. It has a little spot in the corner down there. So that's our, down here. And now what does it look like? Well, you see, when I draw a picture of a black hole, I usually like to draw a space-time diagram. So our time is now going up the picture again. And you see, this is the horizon out here, and there's this horrible singularity in the middle. I want to explain these cones, because these are a crucial thing. The black hole, I should say, represents huge entropy, and by far the largest entropy in the universe we know is in black holes. It's in the biggest black holes that we know about, supermassive black holes in galactic centers. Now, these cones are the most important part of the structure of space-time. These are what we call null cones, or light cones, strictly speaking, null cones. And they represent basically the speed of light, or what light does at any moment. Here's a local picture of it. Suppose we have a point which a flash of light occurs. You imagine that flash is inhabiting a sphere as it goes out like this. The space-time picture would be this cone. I'd have to throw away a dimension to make it work. And the slices through this cone represent this history of these spheres going out. That's the null cone. You might have a flash coming inwards too. I'm not saying there is a flash of light there. It's that's what a flash of light would do if there were one. And so this space-time has these little cones pictured all over it. The final picture is just saying, well, it's really locally, it's in what's called the tangent space. Don't worry too much about that. But the cones are all over the place, and they represent the most important part of the structure of space-time. It's not quite all, though. In Einstein's theory, you have a thing called the metric, and this metric is defined at each point of the space-time. And the metric is a thing which has 10 components. So you need 10 numbers to describe where it is and what's going on. 9 of them describe where the cone is, and the 10th one describes the sort of scale. And how do you measure the scale? Well, you need clocks. And the idea is you have the history of several clocks going through that point. We now have extremely precise clocks, and these clocks tick away at rates which are, to them, equal to each other. But on the space-time picture, it depends on how they're moving. So the first of these bowl-shaped surfaces, the lowest one, is the first tick. Just above it is the second tick and the third tick. And that's the ticks of the clocks. And how densely packed these cone surfaces are is the rest of the metric. That's the last number you need. Now, it's useful to distinguish these things because if I just have the cones, it's what's called the conformal structure. Conformal means that you know angles, but you don't know distances. Or in this case, you know the light cones, but you don't know the scales. You don't know how the clocks behave, but you know where the speed of light would be, or what the speed of light is anywhere. And this tells you the curious geometry of the black holes which trap things inside them and so on. Now, this is the point is now I want to make here, is that we do have these very, very precise clocks in nature, which I think I mentioned before. And these, why do we have such good clocks? Well, the basic reason is that they're the two most fundamental equations, or most famous equations, I should say, of 20th century physics. One of them, of course, has to be Einstein's E equals mc squared, and the other one is Max Planck's E equals h nu. H is Planck's constant, nu is the frequency. So Einstein tells you mass and energy are basically the same. Planck tells us mass and frequency are basically the same. Put the two together, you see that Einstein-Planck tells you that mass and frequency are the same. Well, there's scale factors, which are the velocity of light and the Planck's constant, but they're basically the same. Another way of saying that is if you have a clock, if you have a particle, a stable particle, that stable particle is a clock. It's a tremendously precise clock because these are very basic principles of physics, and this clock is very, very fast frequency, but it has a natural frequency just dependent on its mass and the ideas of quantum mechanics. So you think of the world line of that particle, that's this curve here, it's like it's got a little ticking away along its curve. Now the converse of this is what gives you the geometry of space-time. The clocks determine. You see, it's a very good thing to have the clocks, and it used to be that people talk in terms of little rulers, and rulers were the way you measure distances. They're not really good things for measuring distances. One reason is they're not accurate enough, and in Paris you have the meter rule, which used to be the meter. Nowadays the meter is a certain number of a certain tiny fraction of a second, which the time it takes light to get along the meter. It's much more precise, much better now. So clocks give you distances. That's the point I want to make. So you've got the scale if you've got clocks. The converse of that is if you don't have clocks, you don't have the scale. So if you were thinking of photons, suppose you had a photon, the photon zips along the light cone, it never even sees the first of these surfaces. Photon doesn't tick, it doesn't even make its first tick. It doesn't see the passage of time at all. So if you only had things without mass, primarily photons, it's also true if you, well, let's say photons, then they would not be interested in the passage of time at all. But they are interested in the light cones. That's the only thing that is what they're interested in, if you like. Maxwell's equations, the famous equations that I mentioned them before, but that describe electricity, magnetism, and light, have this invariance that if you change the scale, you don't notice the thing. They just need to know where the light cones are. They don't need to know the scale. Now here I have a picture, a wonderful picture due to the Dutch artist M.C. Escher, and it illustrates a very nice kind of geometry. It happens to be hyperbolic geometry. Don't worry too much about that. The point is that we have these fish creatures, and they are representing this kind of hyperbolic geometry. You have to imagine that according to the geometry that the fish respect, do it the right jumps. There we go. The geometry that the fish respect, they don't know how big they are. So that the fish that look as though they're near the edge are, to them, just the same as the ones in the middle. And it's conformally represented. You could see this most blatantly, but the eyes of the fish are circles. And this means that no matter how down close to the edge, they're still represented as circles. According to the fish, this universe is infinite. But according to us, if we represent this world in this conformal way, so the angles are correctly represented, the angles on the fish's wings, if I can call fishes to have wings, the fish's wings have a definite angle, which is the same, right the way down to the edge. So it's a conformal picture. But what's nice about this picture here is you've got infinity in it. The whole universe of these creatures is represented in this finite way. So you see the infinity is squashed down in this conformal way, very accurately, beautifully accurately done by Escher, in this conformal way, so that you have to imagine the infinite number of fish right up to the edge. But the geometry anywhere is conformally the same as anywhere else. Now I'm going to imagine you do the same trick to the universe. And if it's in the very remote future, well, I mentioned about the black holes disappearing by Hawking evaporation in about a googol years or so, then they're all gone. When you have nothing but black holes, that's what I call the boring era. When the black holes are all gone, that's the very boring era. And it really is boring. But I was worrying about that one day, about how boring it was going to be in those days. I don't quite know why. But then I thought, well, it's not so bad, because, well, who's going to be around there? Not us, but mainly photons. And it's really hard to bore a photon. For two reasons, because probably they don't have experiences, but that's not what I mean. The point is that they don't register the passage of time. To a photon, now to infinity is zip nothing. It's there as though no time had passed at all, and to it, no time has passed. So this will now apply to a universe which is essentially, its content is essentially photons, because then it doesn't care about infinity. Infinity is just sitting there waiting for it to be intercepted by the photons. But that was the view I had from some while back while I was thinking about gravitational waves and how you describe them and so on. But that's an idea which I played around for a while. And now in this cosmological context, think about this picture now, but think about this below this horizontal curve. Below that represents the remote future, and these light cones sort of keep right going on to infinity. And now I'm imagining that there's something outside, beyond infinity. And if you were a photon, you'd go zipping through, and you wouldn't care much about this boundary separating this from this other world. But what's that other world? Well, now here's the crazy idea. Remember I said the Big Bang was something very special, and you could measure its specialness as something like 1 part in 10 to the 10 to the 124. Now that's a great nuisance in some ways. Well, it's not a nuisance, that's not the right description. But rather than trying to explain it, I started by worrying about how you describe it. And I had a thing called the Weyl curvature hypothesis. I'm not going to describe what that is, because I don't need to, fortunately, because my colleague Paul Todd came along and had a much neater way of saying the same thing, which is to say, when you go back to the Big Bang, rather than the squashing down I'm doing to infinity, you stretch it out. And those universes which can stretch out and make a very nice, smooth beginning are the ones we should be thinking about for our universe. Well, that's fine. It was a nice mathematical idea. Here's the crazy idea, that this is what you get. After the Big Bang, after infinity, you get somebody else's Big Bang. Or if that was our Big Bang, before our Big Bang, we got somebody else's infinity. And so this is the picture that I now have. Think of the one here, if you like, the third one up, as us. That's our eon. I call it an eon. That represents from Big Bang to indefinite expansion. And I'm not having inflation. You could say there is a sort of inflation because the inflation was the exponential expansion of the eon prior to ours. I should say this is, I mentioned Veneziano a minute ago. He had an idea like this, and I'm sort of borrowing part of his idea here. I think it's a very interesting and powerful kind of idea. So I'm thinking now, by this Veneziano type idea, that there was an eon prior to ours, and that's where the exponential expansion took place. Not in our eon at all. It was you're looking through, in a sense, to the one before. Now, I'm using both tricks here, stretching out the Big Bang, which you can only do in, roughly speaking, 1 in 10 to the 10 to the 124 cases, very rarely, but it would come about naturally if it was the continuation of the infinity of the one before. And Helmut Friedrich has a very beautiful theorem which tells you that if you've got one of these universes with a cosmological constant, that is the dark energy is sometimes called it, and I talked about that a little earlier on, this expansion, this uniform, this exponential expansion. If it has that, then you can smooth it, you can shrink it down in this conformal way until it makes a smooth surface. And the crazy hypothesis is that that continues to the Big Bang of the next one. And they all line up in this way to make the continuous with it goes smoothly with respect to the conformal geometry. It's the light cones carry very nicely. You do have to do something drastic with the matter, or the mass measurements, and that the idea is basically that at the Big Bang, you don't have to worry because energies are so big that mass becomes irrelevant. And the other end, you don't have to worry, you say, because basically there's nothing there, largely photons, nothing there but things without mass. There's a bit more to the argument than that, but that's the basic idea. And when there's no mass around, the geometry of relevance to the universe is the conformal one. And so a picture like this may not be perhaps so crazy as it looks. But then I say, it's fantasy, sure, but we need a bit of fantasy. The hope is that it's the right fantasy. Maybe it's the wrong fantasy, but I think we need some fantasy of some kind. Thank you very much.
Thank you very much. So maybe I should explain, we heard the word book many times in this lecture, and the title of this lecture is also the title of the last book by Roger Penrose. This is how this book looks like in English. And here are some leaflets after the lectures. If you are interested, you can take some of them. Let me add that this book is being translated now to Polish, and next year it will be available to anyone around. So that's about the book, and well, it's already quite late. Maybe we can have like 3 questions if someone would like to ask some question. There is one on the left.
Did we have one? It's all right. Don't worry.
Hi, I've got one really short question. What was your actual purpose while giving this lecture?
What's my purpose? Well, I should say I was asked to give a popular talk, and I didn't say no. And if I want to give a popular talk which comes easily to me, since I've been giving talks in the United States advertising my book, and I have all these slides ready for me, I can give a talk reasonably easily. If you want to know, I also like the idea that the press does well out of my books because I make a little bit of money out of the books, but that's not the primary purpose. I'm hoping, of course, that people, this is not just a lecture, but I'm hoping that by the book, people will get inspired. Well, it's not, I think I'm trying to say that one should be cautious about some of the ideas in fundamental physics, and that maybe we're not quite on the right track. And it's something that I felt for some while. In my fatter book, which is about twice as fat as this one, The Road to Reality, I did describe these ideas, but without saying, you know, I don't believe them. I was expressing many of the things which I'm expressing here too, but this has got a different basis. I'm trying to say, be cautious about some of these ideas which are presented in a way that we know that some of science is so incredibly precise. We know that even Newtonian theory is extraordinarily precise. Einstein's general relativity has an unbelievable precision that I'm sure even Einstein would have been surprised by. I mean, he didn't like some of the ideas that his theory led you to believe, like black holes and gravitational waves even. They were things he was cautious and didn't altogether take on board. So these are wonderful theories, and I think that people should learn about them and understand them, but also with caution, because quantum mechanics, magnificent theory, I'm trying to say, but it does have its limits. And I'm trying to say to people, look, the craziness of quantum mechanics is not entirely because the world is crazy, which it is to some degree, but sometimes the craziness comes because it's not logical, because quantum mechanics is inconsistent with itself. And rather than trying to say, we should do something about it, which is what I'm trying to say, we should do something about it, rather than that, most people say, oh, well, we've got to try and understand it. And I don't think you can understand it because it's self-inconsistent. So it's this kind of thing which I'm trying to say to people. Yeah, physics is wonderful, and a lot of the mathematics is wonderful too on its own, and I hope people will get excited by these ideas, but don't always take the authority that you're presented with as being gospel truth.
Okay, thank you. Is there another question? Here's one.
Yes, I have a question. Does any of these ideas you've mentioned have any potential to, in some way, influence our technology, or is just pure pursuit of the truth and fundamental understanding of the world, or can it actually, someday have some practical application to technology or development or things like
I think
this?
one of the ideas here, one of the points I'd make here is if you drive your car, well, most people when they drive their cars have a device in them which tells them where they are, where to go, and a GPS system. This depends, it wouldn't work without general relativity. It wouldn't work without quantum mechanics. The basic ideas, quantum mechanics in a way, you can see there's an awful lot of technology, the computers and so on, depend on features of quantum mechanics. What is more remarkable here is this idea of Einstein's that we had to understand gravity all over again. I mean, Newton had a marvelous theory of gravity which works extraordinarily well for most of what one does with space travel as well as on the Earth. But there are limits to it, and Einstein didn't think of applications, I'm sure. He wanted to have a theory which extended the ideas of relativity that were manifest in his special theory, and that was beautiful development too, but not so revolutionary because lots of people had ideas very much at that time. It was just what happens when things move with uniform speed. But Einstein had the idea of extending that to accelerations. And that was the magic idea which led to general relativity. And the mathematics that had been done had already been there. I mean, had been there from the previous century. Riemann, or Gauss, particularly Riemann, and the Italian differential geometers who followed him, they had a scheme which could, well, Einstein had to rely on his colleague Marcel Grossmann to tell him all the mathematics. Then when Einstein grasped it, he realized how to use it. Without that mathematics, he wouldn't have been able to produce his theory. So what was the point of that mathematics, you might say? It was not being done for any useful purpose. Then Einstein used it for his theory. Then you say, what's the purpose of Einstein's general relativity? Okay, there are little corrections to things that you don't get from Newton, but then you wouldn't drive your car with the GPS. So these applications are not part of the intention of the theory. That isn't why Einstein did it. I'm sure he would have had no idea about that. The technology that came about afterwards came about through different routes. But I guess the Einstein input was largely more on the quantum side there. But likewise, why should one explore more about the nature of the world? Well, the initial motivation is we don't want to know about the world. We want to know what's going on. And often people want to know where it came from. After all, did it come from just a bang out of nothing? Or was there something already there? And these issues are things that we just want to know about. I mean, I want to know about them, and whichever scheme turns out to be right, I mean, I'm hoping it's the one I just talked about at the end on the picture here, but that's just because I rather like it for other reasons, apart from the fact that it's the scheme I've put forward myself. So I think there's a lot of it, the motivation initially is you just searching for truth. And then what it's used for is often something quite unexpected.
Okay, so the last question.
What would you predict to be the next big discovery in physics?
Yes. Well, yeah, I think what's waiting to be discovered is this what happens to quantum mechanics. See, people talk about quantum gravity. It's one of the big topics. You say one of the big unknowns in current physics. We have quantum theory, we have general relativity, they don't fit very well. We have to have a theory in which quantum mechanics is applied to general relativity. That's called quantum gravity. The string theorists have one way of doing it. The loop quantum gravity people have another way of doing it. In my view, although each of these has its virtues, in my opinion, the loop one has more virtues because it's more plausible as a picture of the world. But I don't think either can be right, because the real virtue in combining quantum mechanics with general relativity is making quantum mechanics consistent, because it has these two, the unitary evolution, the Schrödinger equation on the one hand, and what you do when you make a measurement on the other, and they are just inconsistent with each other. People try to make them consistent, but they're led along routes which I think aren't helpful. Now that, I think, is not far off as regards experiments. I think it's very likely that within the next decade we'll have evidence which will either refute or support the idea that there has to be a limit to the quantum state evolution, unitary evolution, which has to do with gravity. Now that's not a theory. Usually you have the experimental evidence first before you can see what the theory is. It may be that somebody will come along with a new theory which is the right way of combining quantum mechanics with general relativity, and which in my view will involve as much modification of quantum mechanics as it will of the structure of space-time. So it's something of an even-handed marriage where the impact on experiments will be on the side of how quantum mechanics is modified, not on how general relativity would be modified, just because of the scales involved. These are things which are at the borderline of what we can do now. And it may well be that this will have implications. And people sometimes say, well, we've got wonderful computers. One of the big developments will be quantum computers, which take advantage of quantum mechanics. But then are there limits to what you can do with quantum mechanics when you get systems which are too massive to whatever it is, and you need beyond quantum mechanics? Well, I think that's quite possible. And maybe one can harness these ideas, but then you probably would need the theory. I have also crazy ideas, which I didn't mention here, that it may have something to do with the brain, where the brain works, but that's another topic. I think it's quite possible that there will, within the next, let's say, 30 years, quite possible, that there will be a new theory which replaces quantum mechanics and makes it make sense and consistent with the general principles of general relativity. I do believe it would have to be a major revolution. It's not going to be just tinkering with current quantum mechanics. It has to be a real change of point of view, in the sense that Einstein's theory, you might say it's tinkering with Newton's theory. The effects initially are a little bit just the perihelion of Mercury. You have to correct the motion a bit. But now we have black holes. It's not tinkering. It's a completely different point of view. And I think we need something which is a completely different point of view with regard to quantum mechanics. So that's where I'd put my money, but I probably won't be allowed to collect it or pay, I'm afraid.
Okay, well, let us thank Roger Penrose again.
Oh, that's lovely. So much.